The next is potential energy of dipole. Potential energy of electric dipole in uniform electric field. Potential energy of electric dipole in uniform electric field. So this is a uniform field. So in this uniform field, Fatima, I just have started this topic, potential energy of electric dipole in uniform electric field. So in uniform field, I place the dipole. Let's say this is the dipole. Fatima, what do you mean by dipole? What is electric dipole?
When two charges are equal and opposite.
I'm having two equal and opposite charges, right? So this is the dipole moment. I'm not showing charges, that's the dipole moment. And this dipole is placed at an angle theta. So Juvena, what will happen with this dipole? If you place the dipole at an angle theta with the field, what will happen with the dipole? Will it remain at rest or it will experience something?
It will experience.
What? It will experience what?
It will experience force.
Right. Not force.
Flex.
Torque. Electric field will exert a torque on the dipole. Electric field will simply exert a torque on the dipole. And that torque is given by this expression. Torque is the cross product of P and E. This is the expression of torque. The torque experienced by dipole is P cross E, it's P cross E. Angle between P and E is theta. So that is PE sine theta. That's first equation. So the torque experienced by dipole is PE sine theta. That is the expression. This torque will try to rotate this dipole along the clockwise direction. But I want to rotate this dipole in a direction which is exactly opposite to that of P. I just want to rotate this dipole in a direction opposite to that of P. So initially, let's say dipole was at this angle. Now I will rotate it like this. So this is the direction of dipole moment. This is the direction of electric field. This angle is theta. So we are rotating this dipole from angle theta 1 to angle theta 2. We are rotating this dipole in anti-clockwise direction. So when the dipole is at angle theta 1 with respect to field, it will interact with field, and due to that interaction, this dipole will have some potential energy U. When this dipole is at angle theta 2 with the field, it will again interact with the field and it will have some potential energy U. We have already did in the first class of potential energy that whenever two charges interact with each other, due to interaction, that particular charge will have some potential energy. Here, instead of a charge, we have dipole. Your dipole will interact with field, and due to that interaction, the potential energy is U1. When dipole is at angle theta 1. When dipole is placed at an angle theta 2 with the field, the potential energy is U2. You're supposed to calculate this change in potential energy. To calculate this change in potential energy, that is U2 minus U1, you need to calculate work done in rotating dipole from theta 1 to theta 2. Okay, now tell me. This torque is acting in clockwise direction. This torque is acting in clockwise direction. So can this torque rotate dipole in anti-clockwise, or you need some external torque? Can this torque due to electric field rotate dipole in anti-clockwise direction, or you need some external torque?
We need some external torque.
You need some external torque. So external torque to be applied. So you need to apply an external torque. So an external torque to be applied, tau external, is exactly minus of torque due to electric field. Both the torque would be in opposite directions, but their magnitudes are same. So tau external is minus of tau. That is equation number 1. Or I can even open this cross product. So Jubina, if I open this cross product, what would be the final result? If I open P cross E, the final result? PE, good. PE sine theta. So that's my first equation. And this torque is acting in clockwise direction. This torque is acting in clockwise direction. Now we need to apply an external force on the dipole to rotate it from angle θ1 to θ2. That external torque is in a direction which is exactly opposite to that of θ. So tau external is minus of tau. So if I calculate the magnitude of external torque, then magnitude of external torque is equal to magnitude of torque due to field. That's equation. We can substitute 1 in 2. If we substitute 1 in 2, then tau external will comes out to be P sin theta. P sin theta, that is equation. So this is the external torque acting on the dipole, which is P sin theta. Now you need to calculate work done by external torque, work done by external torque to rotate dipole from inclination θ1 to inclination θ2. So that work done by external torque, the formula of work done is it's integral of tau external d theta from θ1 to θ2. This expression is of class 11. This was in class 11 syllabus. That if you are calculating work done by force, then that work done is F dot dx integral. If your work done is by torque, then that is torque into angle from θ1 to θ2. That is equation number 4. So I'm using this expression from class 11 syllabus. That work done is torque into angular displacement. Now, if I substitute 3 and 4, then you will get that work done by external torque will be its integral from θ1 to θ2. Tau external is Pe sin theta t theta. So work done by external torque is, you can take this Pe outside this integral sign. This is only θ1 to θ2. Afroza, what is integral of sin theta? So we have discussed integration of sin theta earlier. Okay, so open question for all. Afroza, Fatma, Jubena, what is integral of sin theta? Okay, no one remember, huh? Yes, not cos theta, Fatma, this is minus of cos theta. Integral of sin theta is minus of cos theta, limit is from θ1 to θ2. Okay, if I solve this integral, then work done is minus of Pe, its integral of cos theta, limit is from θ1 to θ2. So this is the work done by external torque. Work done by external torque is, it's minus of Pe, it's cos θ2 minus cos θ1. So this is the expression of work done by external torque. And this work done by external torque is exactly equal to potential energy difference. This work done by external torque is equal to potential energy difference. This is how we calculate potential energy. Potential energy difference. So potential energy difference delta U is equal to final potential energy minus initial. It's U2 minus U, which is equal to work done by external torque, which is, so your potential energy difference delta U is minus of Pe cos θ2 minus cos θ1. This is how we calculate potential energy. And this is the expression of work done by external torque. Work done by external torque is minus of Pe cos θ2 minus cos θ1. But if I want to calculate work done by electric field, work done by electric field, we want to calculate work done by electric field now. So here, work done by electric field is exactly negative of work done by external torque. Work done by electric field is exactly negative of work done by external torque. The reason is the torque due to electric field is clockwise, but the torque due to external torque is acting in anti-clockwise direction. So both the torques are acting in opposite direction, so their work done will differ by a negative sign. So you can say that your work done by electric field is negative of this thing. It's minus of PE cos theta 2 minus cos theta 1. So work done by electric field is, it's PE, it's cos of theta 2 minus cos theta 1. So this is how we calculate work done by electric field. Now, after one work done by electric field, he can ask you to calculate potential energy. He can ask you to calculate just potential energy. So, Jubena, this is potential energy or potential energy difference?
Potential energy difference.
Potential energy difference. Let's name these equations. Let's say this is equation number 1, this is equation number 2, and this is equation number 3. In equation number 2, we have calculated potential energy difference. But instead of potential energy difference, if I ask you to calculate potential energy, means you did not calculate the difference between two potential energies. You need potential energy at a particular angle. So to calculate potential energy, we can use equation number 2. Using equation 2. So using equation 2, potential energy difference is, it's minus of PE, it's cos theta 2, it's minus cos theta 1. See, delta U means it's U2 minus U. It's U2 minus U. If I multiply with this minus PE here, let's keep this negative sign inside. This is PE cos theta 2 minus PE sin theta 1. Oh, sorry, not sin. PE cos theta 1. Okay, can you guess the contribution U1? Okay, which one is U1 out of these two terms and which one is U2? Fatma, can you guess which one is U1 out of these two terms and which one is U2?
U2 is PE cos theta 2 and U is PE
sin theta cos theta 1. Okay, Afroza, can you guess the value of theta 1 for which U1 is 0? I need just U2. So let's choose a value of theta 1 for which U1 is 0. 90, very good. If I consider theta 1 to be 90 degree, that means initially your dipole is perpendicular to field. Then your U1 comes out to be 0 because cos 90 is 0. Theta 2 could be any angle. And we can write U2 as U now, because if U1 is 0, there's no point in writing U2. If I make these substitutions here, you will get U minus 0 is minus of PE cos theta minus PE cos 90. Cos 90 is 0. So your potential energy is simply minus PE cos theta. This is how we calculate potential energy. That's minus of PE cos theta. So there's difference between these two relations, relation number 2 and relation number 4. In relation number 2, you are calculating difference in potential energy in two orientations. The first orientation is when your dipole is at an angle theta 1 with the field. The second orientation is when your dipole is at an angle theta 2 with the field. But here, this is equation number 4. There's just one orientation, means if your dipole is placed at an angle theta with respect to field, then your potential energy is minus of PE cos theta. So for the point of view of numericals, these 4 expressions are important. The first one is work done by external torque. The second is potential energy difference. Then third, work done by electric field. This is work done by electric field. And also the potential energy, not the difference, just the potential energy. Then there are some special cases like case 1. Case 1 says if dipole moment is parallel to field. If dipole moment is parallel to electric field. If your dipole moment is parallel to electric field. So this is electric field. And your dipole is placed just parallel to field. Can you guess angle between electric field and dipole moment? What is the angle between? Yes, P and E are parallel. That means angle between them is 0 degree. So if I calculate potential energy, this comes out to be minus of PE cos 0. Cos 0 is 1. So potential energy is minus of P. Your potential energy is minimum. So if your dipole is parallel to field, then your potential energy is minimum. This is minus of PE. The minimum value of minus of PE cos theta is minus P. Because it's negative, So it would be negative, it will be minimum if your cos theta is maximum. So the maximum value of cos theta is 1. So we can say that this minus of PE is the minimum value of minus of PE cos theta. And when your potential energy is minimum, your equilibrium is stable equilibrium. We have already discussed equilibrium 2 times in chapter number 1. One when we're doing equilibrium, and second when we're doing torque on a dipole in uniform. So earlier we decided stable or unstable equilibrium by just disturbing your system. Now we are deciding stable or unstable equilibrium just by looking potential energy. If potential energy is negative, or if your potential energy is minimum, then your system is in stable equilibrium. If potential energy comes out to be maximum, like in case 2, if I say that if dipole moment is anti-parallel to field, is it clear? The first part, case 1, the case when the P and E are parallel. Let's start with case 2. If dipole moment is anti-parallel to field, dipole moment is anti-parallel to field. Anti-parallel means they're acting in opposite directions. This is your electric field. The dipole moment is acting in exactly opposite direction. This is the direction of dipole moment. So if they're acting in opposite directions, that means angle between them is 180 degrees. So if we calculate potential energy, it comes out to be minus of PE cos 180. Cos 180 is minus 1. So potential energy is minus of PE cos 180 is minus 1. So potential energy comes out to be plus P. So you can say that your potential energy is maximum. And when your potential energy is maximum, this is case of unstable equilibrium. Then it's case 3. If your dipole is perpendicular to field, case 3, if dipole moment is perpendicular to field. If your dipole moment is perpendicular to field, means if this is electric field and this is your dipole moment T, angle between them is 90 degrees. So theta is 90 degree here. If we calculate potential energy, it's minus of PE cos 90. So potential energy is 0. It's neither minimum nor maximum. It's in between minimum and maximum. So if your potential energy is neither minimum nor maximum, that means your system is not in equilibrium. This is not the case of equilibrium. So there's no point in deciding stable and unstable equilibrium for this case. Stable and unstable are type of equilibrium, but in case 3, there's no equilibrium. So you won't write this as stable or unstable. So that was about potential energy of dipole in a uniform field. So first thing is you need to calculate work done by external torque, then work done by electric field, then potential energy difference, then potential energy, and then these cases of equilibrium. Solve one numerical based on this concept. An electric dipole of moment 2 coulomb meter is placed in uniform electric field of 5 Newton per coulomb. Uniform field of 5 Newton per coulomb. Calculate first part. Work done by external torque to rotate dipole from position of stable equilibrium to unstable equilibrium. So from position of stable equilibrium means your initial angle is 0 degree. To unstable equilibrium means your final angle is 180 degree. Second, hence calculate potential energy difference. Third, also calculate work done by electric field. potential energy if dipole is placed at 60 degree with respect to field. You have to calculate potential energy if your dipole is placed at 60 degree with respect to field. So in the first part, you're supposed to calculate work done by external torque. So work done by external torque is simply minus of PE, it's cos of theta 2 minus cos theta 1. Next, we can substitute the values. P is 2. Okay, good. E is 5. It's cos theta 2. Theta 2 is 180. Theta 1 is 0. So work done by external torque is, it's minus 10. Cos 180 is minus 1. Cos 0 is minus 1. So work done by external torque comes out to be 20. It's not 10, it's 20. Second. The next is potential energy difference. So here, potential energy difference is exactly equal to work done by external torque. You can simply write that potential energy difference is equal to work done by external torque. So you can write potential energy difference is 22. That's it. Third one. The next is you need work done by electric field. Johanna, is it clear? Work done by electric field is just negative of work done by external torque. So work done by electric field here is minus of 20. That's the third part of the question. Part 4. The last part is you need potential energy if dipole is placed at 60 degree with respect to. So if dipole is placed at 60 degree, then potential energy is minus of PE cos 60. So potential energy is minus of P is 2, E is 5, cos 60 is half, gets cancelled out. So potential energy is minus of 5. So that was about potential energy of dipole in uniform electric field. Okay, after potential energy of dipole, the next is electrostatics of conductor. The next topic is electrostatics of conductor. That's the second part of chapter number 2 is divided into 3 parts basically. The first one is potential and potential energy. The second is electrostatics of conductor and dielectric, and the third one is capacitance. So that's basically the second part, electrostatics of conductor. Let's start with conductor. So what are conductors? Conductors are materials which can conduct electricity. Conductors have free electrons. All properties of conductors are due to free electrons. If you have conductor have positively charged ions. They have positively charged ions and free electrons. All properties of conductors are due to free electrons only. So conductors have free electrons which are responsible for electric conductivity. So all properties of conductors are due to these free electrons only. These electrons are absolutely free to move within the body of conductor. These electrons are free to move within the body of conductor, are free to move within the body of conductor. So these electrons are absolutely free to move within the body of conductor. They can move freely throughout the body of conductor. And all properties of conductors are due to these free electrons only. So let's start with some properties of conductor. Properties of conductor. Okay, first property. Giovanna, what should be the net charge inside a conductor? A conductor is negatively charged, positively charged, or is it neutral? Giovanna?
So it's neutral.
Neutral. It has equal amount of negative and positive charge. So net charge inside a conductor is 0. Now, if I charge a conductor, I take a conductor, and provide charge over this conductor. I'm providing some extra charge over the conductor. Then this charge will always resides only on the outer surface. If you try charging this conductor, then charge will reside only over the outer surface of conductor. There won't be any charge inside the conductor. Even if you charge a conductor, and charge will reside only on the outer surface. Even now, the net charge inside the conductor is zero. This is property of conductor. Whenever you try charging a conductor, that charge will reside only on the outer surface. Inside the conductor, net charge is always zero. Charge resides only on the outer surface of conductor. So charge will reside only on the outer surface. There is no charge inside the conductor. The net charge inside the conductor is zero. Just note it down, then we'll do some more properties of conductor. Both the next topic, capacitance, as well as chapter number 3 are based on conductors. We will use these properties of conductors even in chapter number 3 in current electricity. Okay. So that's the second property of conductor, that net charge inside a conductor is zero. Even if you charge a conductor, that charge will reside only on the outer surface. There is no charge inside the conductor. Third property. Electric field inside a conductor is zero. Electric field inside a conductor is zero. Is zero. If you have a conductor, charge will always reside on the outer surface. Inside the conductor, charge is zero. If charge is zero, then it can be proved that electric field is zero. We can prove it using Gauss law. If I consider Gauss law, using Gauss law, let's consider a closed surface. Then Gauss law says closed integral of E dot ds is Q enclosed by epsilon naught. So if your Gaussian surface is within the conductor, then inside that Gaussian surface, the net charge is zero because Q enclosed is always zero. Q enclosed is zero. If your Q enclosed is zero, that means closed integral of E dot ds is zero, which simply means that electric field inside the conductor is zero. So the simple two-line proof that if charge inside a conductor is zero, then according to Gauss law, electric field is always also zero. Fourth one. So electric field inside a conductor is zero. The next is electric field is perpendicular. Electric field is perpendicular to surface of conductor. It's perpendicular to the surface of conductor, and its value is sigma by epsilon. So electric field is always perpendicular to the surface of conductor, and its value is sigma by epsilon. So if I consider a conductor of any arbitrary shape, say positive charge is distributed over the conductor, then the electric field is always perpendicular to the surface. Then it's sigma by 2 epsilon. Sorry, sigma by epsilon. N cap. N cap simply shows it's perpendicular. N cap is a unit vector which is perpendicular surface. What if it has more than one surface? Fatma, it doesn't matter the number of surface this conductor has. You can have a conductor in this way, right? This have multiple surfaces. Electric field on each surface would be perpendicular to it. If it is conductor, then electric field is always perpendicular to the surface of conductor. That's it. It's absolutely independent of the number of surfaces. By the way, what is sigma here? Afroza, what is sigma? What sigma represents?
Is it surface charge?
Yes, this is surface charge density. Means charge per unit area. We will prove this property using Gauss law only. So let's consider a conductor of some arbitrary shape. The charge is distributed only on the outer surface. So the surface charge density of this conductor is plus sigma. The charge here is distributed only on the outer surface. So the surface charge density is plus sigma. To calculate electric field, as we have discussed, it's perpendicular to the surface of conductor. It's always perpendicular to the surface of conductor. To calculate this field, let's consider a cylindrical Gaussian surface. Consider a cylindrical Gaussian surface. The area of the end is delta S. I have placed the cylinder in a way that the top surface of the cylinder coincides with the surface of the conductor. The rest of the cylinder is inside the conductor. Only the top surface coincides with the surface of conductor. The rest of the conductor, the entire conductor is within the conductor. Entire this cylinder is within the conductor. Johanna, can you just tell me what is the value of electric field here? At this point of cylinder, the value of electric field? 0. Very good. Because this point is inside the conductor. So inside the conductor, your field should be 0. So let's consider. A Gaussian surface having area of ends delta S. So let's consider a Gaussian surface. The area of the ends is delta S. First of all, let's calculate flux to the top surface. Let's calculate flux through the top surface. The direction of the top surface is perpendicular to the surface as area vector. This we did in chapter number 1 in Gauss law. That direction of area vector is always perpendicular to the area. So this area vector and electric field are acting in same direction. So flux through top surface, let's call this flux as delta phi. This flux is E dot delta S. Afroza, what is the angle between E and delta S here? Afroza. S is area, Fatma. S is area. Delta S means small area. That's the area of it. So Afroza, what is the angle between E and delta S? Okay. Fatma, what is the angle between E and delta S? The angle between E and delta S. What is the value of angle between them? It's not 180. No, it's not 90. See, electric field is perpendicular to the surface. Area vector is again perpendicular to the surface. They're acting in same directions. E and delta S are acting in same direction. Yes, that means angle is 0 degree. They're acting in same direction. Na? So this is E delta S cos 0. Cos 0 is 1. So your delta phi is E delta S now. That's the solution. Okay. Next, I need flux through rest of cylinder. So Fatma, what is flux through rest of cylinder? This is through the top surface only.
0.
0. Because else than this top surface, the entire surface of the cylinder is inside the conductor. Inside the conductor, the field is 0. There is no field. If there is no field, then flux would be 0. Is it clear, Fatma? Afroza? The rest of the cylinder is inside the conductor. Inside the conductor is no field. No field means no flux. Delta phi 2 is 0. Next, we can calculate the total flux. Total flux delta phi is sum of flux due to the top surface and the rest of the cylinder. Delta phi 2 is 0. So you can say that your delta phi is delta phi 1, which is E delta S. That's equation number 3. That's the total flux. We can even calculate this flux using Gauss law. Now we will use Gauss law. We will use Gauss law for the complete cylinder. So Gauss law says delta phi is delta Q enclosed divided by epsilon naught. Delta Q enclosed divided by epsilon naught. That is equation number 4. Here delta Q enclosed means this is delta Q enclosed. The charge enclosed in this much portion of the cylinder. Charge is distributed over the conductor. The cylinder is intercepting a part of the conductor. So there must be some charge which is enclosed by the cylinder. So you can say that delta Q enclosed is charge on area delta S of conductor. This cylinder is cutting an area delta S part of the conductor. So whatever the charge is on that area delta S, that charge is delta Q enclosed. Next, you can write your sigma as, your sigma is the ratio of charge and area. So you can write this as delta Q enclosed divided by area, which is delta S. You can write your delta Q enclosed as sigma into delta S. That's equation number 5. We can substitute the value of delta Q enclosed from 5 and 4. If I substitute 5 and 4, then we'll get that delta phi is sigma delta S over epsilon. That's equation number 5. Now we can easily equate 3 and 5. Equating 3 and 5. Now, if we equate 3 and 5, we will get E delta S is sigma delta S by epsilon. So when you equate them, you get your E is sigma by epsilon naught. So this is electric field on the surface of conductor. If you remember, we have done this calculation before in Gauss law. We have calculated for a sphere, a solid sphere having some charge Q. Because we get the same result on the surface of the solid sphere. And this result is absolutely independent of shape and size of the surface. See, if you have this is electric field, but instead of a positively charged conductor, if you have a negatively charged conductor, say you have a conductor, here charge distributed is positive, and here the distributed charge is negative. At this point, the direction of field is away from the charge. This is the direction of field. Over this point, the direction of field is towards the charge. This is the direction of field. Field is always perpendicular. But for the positive surface, it's away from the conductor. But if the charge is negative, then it's towards the conductor. The direction of field will change. For positive, it's outwards. For negative, it's inwards. Just draw this diagram. And then we'll do next property of conductor. The next property, fifth property. The fifth now? First, second, third, fourth. Yes, the fifth property. The fifth property is about electric potential. Electric potential is constant throughout the body of conductor. Throughout the body of conductor. It's constant throughout the body of conductor. It has same value on surface and inside. Exactly same value on the surface and inside. Say this is a conductor. If I say that potential over the surface is V, which is 5 volts, then on each and every point of the surface, your potential is 5 volts. Here too, your potential is 5 volts. Even inside the conductor, your potential is 5 volts. So throughout the body of conductor, your potential is constant. That is the fifth property. So can I say that the surface is equipotential? That's the property of equipotential surface. That potential at every point is same. So you can say that surface of conductor is equipotential. Electrostatic shield. Here, electrostatic shielding is the phenomena. It is the phenomena of making a region free from any electric field. It is based on the fact that electric field vanish inside the conductor, inside the cavity of conductor. See, electrostatic shielding means, say you have a conductor, a solid conductor of some arbitrary shape. And that's a cavity inside the conductor. This is the cavity inside the conductor. It's a cavity. The solid conductor, and we make a cavity inside this solid conductor. If I provide some charge to the conductor, then charge will reside only on the outer surface. Charge will reside only on the outer surface. Even if I apply field on this conductor, that field will again resides only on the outer surface. Inside the conductor, charge is 0. Inside the conductor, field is 0. That means this space inside the conductor is shielded from all types of electric fields and electric charge. This property is known as electrostatic shielding. Practically, this property, this electrostatic shielding, can be used to make a space free of electric field. So if you consider a room, even if your room, there are some electric fields, some electric fields are present in your room. The cause of that electric field, the sources of that electric field is mobile phone radiation. There are wires from which current is flowing. That current will produce electric field. Your mobile phone radiation will produce some electric field. So if you want to make a region of your room free of electric field, then what you can do, you can just take a conductor and place around that region. So if in my room, I want to make this particular region free of electric field. There may be some electric fields in this region due to my mobile phone radiation, due to current flowing through the wire. I want to make this particular region free of electric field. So to make this region free of electric field, I will take a conductor around this thing. I can take a conductor around this region. The net field inside that conductor is zero. So just by placing a conductor around the region, we can make this region free of electric field. Once I place the conductor around it, the net field inside it vanishes. It will be zero. This property is known as electrostatic shielding. Fatma asked a very good question that how does current flow through a conductor then? Because current always flows through a conductor and current means electric field. Current flows due to electric field. But that current that flows through a conductor is due to cell or battery or your power supply. That power supply forces the electrons to flow in the conductor. Otherwise, if you don't apply a power supply, the net field inside conductor would be zero, your current would be zero. Okay, just answer one more question. So during lightning, is it safe to sit inside a car or outside the car? So there's thunderstorm and there are chances that lightning could strike on the ground. So what will you prefer, to sit inside the car or outside the car?
Outside the car.
Outside the car. Okay, if you stand outside the car, this is the car, this is the body of car. Yes, car is a conductor, right? Car is conducting, car is metallic body. You are sitting inside the car. In case of lightning, lightning means charge, a very heavy charge. In case of lightning, if lightning strike on the body of charge, then due to electrostatic shielding, all of the charge will reside only on the outer surface. This car will act as a shield. It will act as a cavity. The charge will reside only on the outer surface. It will not enter the body of conductor. But so you won't come in direct contact with the charge. Unless you touch the body of the car, you will not be in any direct contact with the charge. So this charge which is flowing due to lightning cannot harm you. But if you are standing on ground alone, then this charge through the lightning will strike you directly. So it's better to be inside the car than outside. It's safe inside due to electrostatic shielding. That body of car will act as a shield due to electrostatic shielding. Spherical conductor. This topic is not given in NCERT, but in NCERT you will find numericals based on this concept. So we won't derive any result. We will see some direct results. Spherical conductor. So if you have a spherical conductor, it can be hollow or solid. It's a spherical conductor. Charge will reside only on the outer surface. Charge resides only on the outer surface of this conductor. Charge Q. The radius of the conductor is R. The radius of conductor. Let's consider a point outside the conductor. This point is at a separation R from the center of conductor. We're supposed to calculate electric field over this point. First, we are considering point outside the conductor. We have derived the expression of electric field outside the conductor, and the expression of electric field is 1 over 4 pi epsilon naught. It's Q over R square. This is the expression of electric field outside the conductor. It's 1 over 4 pi epsilon naught Q by R square. This is how we calculate electric field outside the conductor. This we have derived in Gauss law. The potential outside the conductor is 1 over 4 pi epsilon naught. It's Q by small r. And remember, this small r is not the radius of the conductor. That is the separation of point from the center of conductor. We have derived this result in Gauss law, but I will not derive it. This is not given in NCERT. Only in some numericals he is using it. So it's important to do this formula, but I'm not deriving it. If you want to derive it, you can derive it using potential is minus of integral of E dot dr. You can just integrate your electric field. The integration of electric field will give potential. Second, you need surface on the conductor. Surface of conductor. Okay, can you people guess the value of electric field and potential on the surface? What will be the difference in the relation? If I'm taking point on the surface, can you guess the expression of electric field and potential? Yes. There will be a very minute difference. Foza, Fatma, Jubaina, Johanna. What would be the difference? No, it won't be E dot ds. I'm just asking about the value of expression of electric field and potential on the surface. What change will be here? When I'm calculating outside, I'm using small r. When I'm calculating on the surface, I will use, instead of small r, what I will use? I will use capital R. Similarly, when we calculate potential on the surface, it comes out to be 1 over 4 pi epsilon naught x cube by r. This is on the surface. This is the value of potential on the surface of it. Third part, inside. Inside the conductor. Can you guess the value of field inside the conductor?
Is it small r minus big R?
Electric field inside the conductor. Just have mentioned, yes. Electric field inside the conductor is zero. That's the second property or third property. If you are taking a conductor, then electric field inside that conductor is zero. Electric field is zero, but not the potential. We have written that surface, the whole body of conductor is equipotential surface. Means potential is same on the surface as well as inside. So on the surface of conductor, your potential is same. Sorry. Inside the conductor, the value of potential is exactly same as that of surface. That is Q by 4 pi epsilon naught R. Remember this result. We will use this result in many questions. Potential inside the conductor, or you can say that at the center is the same thing. Even at the center, the value of potential is Q by 4 pi epsilon naught R. I'm not deriving that result. You have to remember that potential is same throughout the body. On the surface and inside, the potential have same value. That was property number 5th or 6th, I guess. Let's rub it and move on to next question. So you have two conductors. One of radius R1, another of radius R2. The first one, the charge on the first conductor is Q1, and the charge on second conductor is Q. Let's take 2 points, a point A and a point B. Let's take 2 points, a point A and a point B. So you're supposed to calculate the value of potential on point A as well as point B. Calculate potential at A and B. So you're supposed to calculate potential at point A as well as point B. So potential at point A is, so see, both the charges Q1 as well as Q2 will generate potential at point A. So to calculate potential at point A, you have to decide the position of point with respect to charge. I'm solving the first part. Potential at A. Potential at A. So potential at A will be due to both the charges, Q1 as well as Q2. So where is Q1? Q1 is on the surface of first sphere. With respect to Q1, point A is on the surface. With respect to Q1, point A is on the surface. Point A is on surface. So with respect to Q1, point A is on the surface. With respect to Q2, see, Q2 is on the surface of second sphere. So with respect to Q2, this point A lies inside. Point A is inside. Is it clear, these two statements? Because whole calculation will depend on these two statements. We always see point with respect to charge. That with respect to Q1, your point A is on the surface. With respect to Q2, your point A is inside. So potential at A So Joanna, what is value of potential at the surface of A? Sorry, at the surface of first sphere? Potential on the surface of first sphere. We just have it in the formula. Potential on the surface of first sphere. Anyone? That's an open question for all now. What is the value of potential?
Q by 4 pi
Yes, Q by 4 pi.
epsilon R1.
Yes, Q1 over 4 pi epsilon naught R. Because potential on the surface is 4 pi epsilon naught capital R, where capital R is the radius. So the radius of the sphere is R1. Now, with respect to Q2, your point A is inside. The value of potential inside the sphere is same as that on the surface. The value of potential inside the sphere is same as that on the surface. So it's Q2 over 4 pi epsilon naught R. Inside is same as that on the surface. So it's Q2 by 4 pi epsilon naught R. Is it clear? Let's move on to second part. If it is clear, Johanna, then tell me about this potential at B. This is point charge B. So where is B with respect to Q1? Is it inside, outside, on surface? Johanna.
Outside.
Yes, it's outside. Good. And what about with respect to Q2?
On the surface.
On the surface. Great. With respect to Q2, point B is on the surface. So potential at B. So outside, the potential is Q1 by 4 pi epsilon naught, the separation between the center of the sphere and the point. So Joanna, what is the separation between the center of first sphere and the point B? Because it's outside, the outside we use Q by 4 pi epsilon naught small r, where small r is the separation between the center of sphere and the point. So what is the separation between the center of first sphere and point B? Joanna?
R2.
What? It's R1, R2?
R2.
R2, right. So 4 pi epsilon naught R2. And what about Q2? What's the potential at B due to Q2? Q2 is on the surface only, yeah? So it's 4 pi epsilon naught R. This is potential at B. And this is potential on the surface of first. In the third part, do one more thing. Just subtract VA minus VB and try to prove that this is greater than 0. Now let's take your calculation about VA minus VB. You're supposed to prove that VA minus VB is greater than 0. Third part. So VA minus VB. VB is this Q1 by 4 pi epsilon naught R1 plus Q2 by 4 pi epsilon naught R2 minus of Q1 by 4 pi epsilon naught R2 plus Q2 by 4 pi epsilon naught R2. So this will cancel this term, and this VA minus VB is Q1 over 4 pi epsilon naught R1 minus Q1 over 4 pi epsilon naught R2. So VA minus VB is, you can take this Q1 by 4 pi epsilon naught is constant. This is 1 by R1 minus 1 by R. This is VA minus VB, 1 over 4 pi epsilon naught, 1 by R1 minus 1 by R. Next, you can take this, take LCM here. It's Q1 by 4 pi epsilon naught. You can take R1, R2 as LCM. So this is R2 minus R. Now, since outer sphere, the radius of outer sphere is greater than the radius of inner sphere, so you can say that R2 minus R1 is positive. If it is positive, that means VA minus VB is greater than 0. That means VA is greater than VB. This is an important result. Say this result is independent of Q2. Whatever be the charge on the outer sphere, whatever be the amount of charge on the outer sphere, you can put any high value charge on the outer sphere. Inner sphere will always be at higher potential. That's an interesting result. You can see, say this result depends only on Q1. It's independent of Q2. So whatever be the value of charge on the outer sphere, So no matter how high charge is on the outer sphere, the inner sphere will always be at higher potential. Inner sphere is always at higher potential with respect to out. Even this is such an important result that Venn diagram made a generator over this result. This is also known as principle of Venn diagram generator. Although Venn diagram generator is not a part of syllabus now, but earlier it was in syllabus. This is basically principle of Venn diagram generator. So very interesting result that whatever be the amount of charge on the outer sphere, the inner sphere will always be at higher potential. This is known as principle of Venn diagram generator. So that was about electrostatics of conductor. This conductor is very important. You can get direct questions of conductors. Otherwise, you will use conductors in capacitor as well as in current electricity. After conductor, the next is dielectric. This is a theoretical question. If you remember, in the first class of electrostat, you people asked some questions like, what is the physical significance of epsilon naught? I told that epsilon naught is relative permittivity. I told that this is relative permittivity. Someone asked that, what do you mean by permittivity? There's one more very common question that if I place two charges in air, then the force is Fa. What will happen if I place the same charges in medium? Force will remain same or it will decrease? The very generic questions of electrostatics. Like if I take two charges in free space, two charges in air, say you have two charges, a charge Q1 and a charge Q2 placed at a separation r. In air, they repel each other, let's say with a force Fa. If I put the same charges at the same separation in some medium, let's say water, what will happen to force? It will remain same or force will change? Yes, force will decrease. Force in water is less than force in air. Force will decrease. The force is maximum in free space, maximum in air. If you keep on changing the medium, the force keep on decreasing. Why force decreases? How a medium affect the force between the two charges? Or the questions like, if you have a charge, you place that charge in free space. Say the value of electric field is E. If I place the same charge in water, Jubena, what will happen to the value of field? I place the charge in air at a distance some r from the charge. I measure field and it comes out to be E air. I took the same charge, I placed this charge in medium, say water, and calculate field at the same separation. Can you guess how this field will change as compared to E air? It will remain
In water, it will increase.
decrease. In water, field decrease. Not just field as well as force. When you place a charge in a medium, some water on any other medium, the force decreases. But the thing is, how medium affect the force between two charges? How medium affect the field of a charge? That is through this topic. The topic we will discuss now. No, it's not about density of polar. It's not about density. It's about polarization. It's about dielectric polarization. Why electric field inside a conductor is zero? We have proved mathematically that electric field inside a conductor is zero. But why it is zero? What happened with the conductor so that field becomes zero? All these theoretical questions will get answered in this topic, dielectric and polarization. So this topic starts with the concept of dielectric. What are dielectrics? Dielectrics are non-conducting medium. Non-conducting, what do you mean by non-conducting? They have free electrons and they don't?
They don't.
They don't. Dielectrics don't have free electrons. But still they transfer electric effect. So material which can transfer electric effect without conduction. So some materials, some non-conducting materials can transfer electric effect but without conduction are known as dielectrics. The examples include like air, water, CO, carbon monoxide. These are examples of dielectrics. These materials don't have free electrons. They can't conduct electricity. They can't conduct charge, but still they can transfer electric effect from one point to another. So these are known as dielectrics. We will see how dielectric can transfer electric effect from one point to another.